My name is Kevin J. Cull, PM Head of Cloud Management Solutions here at Supermicro. So lately, there's been all this buzz around grid-aware compute and how AI factories are converging. Clearly, the technology is forcing neo cloud providers to think about innovative ways to optimize their tokens, bringing in better ROI for their GPU as a service tenants. Researchers at Ventas and Supermicro have emboldened DevOps administrators with a toolset called Power Grid Manager to orchestrate power workflows based on policies and business rules. Unifying power infrastructure assets with coolant infrastructure assets, where AI factories become virtual power plants, flexible load entities, or power load balancers. I'm super excited to show you what we've been building with Bantos Energy this last 1.5 years. It's been really, really groundbreaking. And we anticipate there will be lots of attraction to our solution that we provided, our combined solution. Our software defined approach does not rely on waiting for any additional hardware to be invented. Importantly, our solution is completely agnostic. NVIDIA, AMD, Intel Accelerated Compute work with our solution. We are able to GPU flex or throttle down GPUs when some event dispatch occurs specific to the grid. In the previous videos, we talked about several different use cases and explained in detail what locational marginal pricing is and how it pertains to the North American energy markets. We talked about neo cloud providers playing the market instead of relying on a fixed cost of energy cost, driving up their ROI and not making any kind of money. Zone boundaries are set up in the European Union markets that auction power supply, sharing a bidding of nodal pricing. Today, Supermicro and Ventus combined solution delivers on this vision of solving the grid power constraints that exist today based on a GPU load shedding methodology. What's important to note that no workloads are evacuated to spare clusters sitting idle, driving up the cost of your AI factory deployments. You can think about this analogy. We're turning down the spigot to a right three-quarter turn, impacting the flow of water to a drizzle. When it's time to affect the water flow, again we turn it back up when we receive a signal telling us to do so. This is great news for energy consumers around the world when they deploy a converged AI factory. With our bold leadership in the industry, Supermicro, Ventas, and C Power are paving the way and have delivered to the world the first to market workable formula that aligns with FERC's vision of regulatory compliance. On June 23rd, 2026, we showcased this live demo in Hamburg, Germany at ISE 2026 venue. The production will be available in the August timeframe of this year for our customers to deploy. If you didn't have a chance to go to the venue in Hamburg, no worries. We have staged two converged AI factories, one in San Jose headquarters and the other one in Den Bosch, Holland headquarters. Let's unpack this solution in more detail and see what we can discover. All right, so I'm sitting here at the dashboard ready to log in here. So we talked about in previous videos how to log into the dashboard, so I'm not going to get into that detail. So I'm going to sign in as a local user, put in my admin credentials here. And I go directly into the front dashboard here, which again is read only. And if you notice here, the menu options are broken down into a PDU console, which we talked about in previous videos, and the Power Grid console. So the Power Grid console is where the intelligence comes in for Power Grid Manager. So before you start, you have to register each of these, what referred to as asset classes, right? So you see here two converged AI factories. One is IP address 10.185.13.124. The other one is 172.31.45.102. So one is in San Jose in the Converged AI factory, and the other one is in Den Bosch in the EMEA headquarters. And then we have various e-tags or tokens that you have to provide so that we license our software that you will have to purchase. And so we'll talk about the business models, and you can reach out to sales on how you can take advantage of this latest features and where we turn on licensing. All right, so I'm going to start with the first one, which is the Converged AI Factory here first. And we talk about LMP, right? Locational marginal pricing. And we talked about the importance if, some particular AI factories that are in some parts of North America may be cheaper, right? And it's based on the power supply and power demand in those zone boundaries, right? So you can see here that maybe in the urban areas, it's very costly to have power, and then out in basically in I'll call it the sticks, or in the other areas, which are the non-urban areas, pretty much are cheaper in price. So this is real live, basically pricing that we are receiving from the grid. So we have a meter that sits on an E403 device, which is one of Supermicro's pole-mounted devices that is collecting this data with also an E-gauge device. And we're seeing here, when you set up these asset classes, you can set them up at a transformer level, you can set up as a breaker level, you can set it up as a rack level, anywhere that you want to collect these important particular information, which is going to be helpful. And we'll see that a little bit later when I show you here. So we show you on the right-hand side the uptime of how we're polling and getting this data. And we talked about the LMP and how the breakdown is based on MCE, MCL, MCC, MGHG. So I'm not going to go into this detail here to explain that, because that was in a previous video. We broke down how the pricing gets derived here. So these are various different stations that we're collecting this particular data from the grid. So it's showing you a decomposition table that shows you LMP pricing on a megawatt itself, right? How much we're paying in each of these particular areas, right? And a breakdown based on each particular variable that impacts the LMP. And then here we have the PUE scores. So a PU comparison between Milpitas, Montague. So these are various different stations, grid stations that exist out in California in our San Jose facility here, where we're collecting this particular data. And then you also see a breakdown of regional power distribution efficiency. You can see here things like wasted power, with real live data that we're actually pulling from the grid. So very important to get oversight in how efficient and your particular NeoCloud is being operated based on power. And then we have regional energy economics here that exist, cost per month breakdowns. So we're getting all this data and we're aggregating this together and showing you the information in this dashboard in San Jose. And we also have breaker level detail, right? So I talked about asset classes, right? Of potentially putting these CT clamps that are connected in line to these particular power sources, collecting the data and providing it visually through visual graphs and displays here within our platform here. And then on the bottom here, you see actually the GPU flex. You see pretty much the server itself is sitting pretty idle. So in the next few videos, we'll show you how we can ramp up the GPU that it's running at peak load. And then when we simulate a demand response, frequency response, or price change, we'll basically simulate that and then force the GPUs to be throttled down, right? And then once that particular price or that demand response dispatch gets sent back to the curtailment service provider, then it'll be safe for us to ramp them back up again, right? So we'll demonstrate that in later videos here. So that's on the San Jose side. So if you hit on the navigation view here, we have ability to pull down what we call analytics. So these analytics are LMP component trends that we've seen that have been time-stamped across deltas, right, that are seeing here. We're collecting here is every period here and showing you the detail by scrolling across here. And then you can look at different ones. You can look at MonoQ2 as well. You can look at also these various substations that exist on the grid showing you that information. All this information is being pulled in real time from the grid as our grade meter exists pulling this data. So you could play the energy markets, right? So that's the key, right? So you don't have to pay your fixed cost of energy. You can play the markets and basically curtail your loads within your NeoCloud at times when the peak of, say, the price per megawatt is a high value, right? And you'll be able to curtail and change based on a strike price. And we'll get into more of those details a little bit later, but you sort of get the idea here. And then we're showing you the PUE here as well itself. So we're showing you power load PU correlation profiles. So we're showing you very inefficient values, inefficient and average. You can see here where it's sitting at the efficient level, which is really good. So we show you sort of a PUE health score, right, of how well you are utilizing your power and load consumption. And then we have our energy pricing insight too as well. You can see dips where the price was going up and down. You can see here the price was fluctuating based on the demand that existed on the grid. And we talked about all those various different variables that sort of affect that particular price, right? And depending on different locations that you are in North America can also fluctuate quite frequently. All right. So that's the energy pricing insight. Let's go down to the e-meter itself, where we're breaking down what we call asset classes itself. And we can look at a breaker level, you can look at a transformer level, so on and so forth. So it's taking a minute here to pull this particular data here. And so just give it a minute here till we pull this data here. All right, so it came back here with our consumption trend. We're talking total power, breaker power. We have different C clamps that are in various different breakers collecting different things. So you may want to think about, putting breakers in a transformer. You may be looking at breakers related to consumption of a cooling tower or breakers associated with how much power you're using versus an in-rack CDU or an in-row CDU. So you can get visibility into various power sources that you're drawing and get a better understanding of how well you're consuming power and optimizing power in your converged AI factory. So you see here three-phase energy rate trends, accumulated energy, local trend and power quality analysis, and accumulated ampere hours. So all these are variables or data that we're actually pulling in real time, and it's broken down here at a breaker level. So we have 4 breakers that we're pulling. So of course the data might be differently depending on the load per breaker. Perhaps you're running different types of workloads that are occupying amount of power. Maybe you're running essentially just business compute that may not be taking up a lot of power. It's basically static in nature. And then you have certainly peaks of power utilization with GPUs, which go up and down and is more erratic in showing that information. So some pretty cool looking graphs. You can go here and look at various information here as you're pulling across each of these particular visualization trends here. And the last one here we're going to show you is the GPU Flex itself. And we're pulling the data for GPU Flex information from the San Jose. So this information is we've been using that as essentially curtailing and simulating in the show at ISC in Hamburg. And you can see here the various different types of peaks that we were basically essentially ingesting into our prototype, simulating basically a demand response, frequencies response, or price change based on the information here. So this is all real time. You can see we've been doing this earlier today. All right, so that is the San Jose Converged AI Factory. So we're going to flip over now to the Den Bosch one here. And where Den Bosch is a little different here is that we talked about nodal cost breakdown and market price overview based on zone boundaries, right? So you see here that we don't have any of the other ones available because we don't have a service program over in Europe, right? It's very regulatory, and as far as electricity is concerned, and they basically share power between each of the countries, right? So it's a little different cost structure over there, and we would not report on any of these various other variables that impact the price. They typically go into an auction type of situation where they auction off and uh, through boundaries and calculate the price there. Or you show here the zone boundary here, a BZN, and then you see here is the price per megawatt in euro. So you can see it's pretty pricey there in Europe. And then you have other PUE and regional stuff here, regional energy agnostics and emitter stuff. So we have different phases over and breakers in our BV lab, or we call it the Netherlands EMEA headquarters, and then also the various different GPU flexing we're doing here. All right, so let's look at the analytics piece of this for LMP. So we're pulling the data, slightly different trends we're seeing here. Remember, we're not seeing any of the other variables here. So they're not showing up in our particular chart itself. And then we have the PUE, which is the power load and PUE correlation profile for energy pricing insight. You can see quite a bit of up and down here across here through Europe as far as our pricing insight is concerned, cost per hour. And then we also have the E-meter here, which is where we do the breakdowns of each of the breakers. You can see breaker power consumption trends existing. You can see the three-phase energy rate trends here, accumulated energy, and we have breaker main, and then we have another breaker here, which is the 1019. So we have differences of load capacity or load consumption on each of these particular breakers. And then the last piece is we're doing our GPU flex. So we can also flex GPUs based on not all pricing, right? But where it's different here in Europe opposed to North America is based on a curtailment, right? A signal that basically gets sent from the curtailment service provider, such as a frequency response, a fluctuation that maybe there is an emergency where there was a blackout occurring or something like that, and there's a signal sent from the curtailment service provider to curtail power. Various different kind of use cases there, and we would set business rules to curtail that from the curtailment service provider. So that service program exists in North America, but does not exist in Europe because of electricity is regulated in the European Union. So here we have it, Power Grid Console. So this is what we brought out as an MVP that we're going to push out in the 313. We'll be building in some additional features here when the 313 release hits in August. But we got this out the door here to really showcase at ISC 2026. So we're delivering on our promise to be able to have a grid-aware compute. Some of the technology partners out there in the industry are talking about it. We're delivering on it. We are the first to market here with our combined solution of CPower, also Ventas and Supermicro. So thanks for joining today. And so that's all I have to show you here. We'll look for additional videos to come where we'll get into more detail, more features that'll be part of the Power Grid Manager. Thanks for joining today. We'll see you next time.